Okay, I am back. So this project called Forest to Facade is a project that I unfortunately uh, included all the project contributors at the very end of this slide deck, but I want to just initially mention that this was a very collaborative project, especially working together with Swinnerton doing cost estimation, Oregon State doing the structural seismic analysis, and FFA working with us on all the details and architectural expression. And so anyway, I'll go through all those contributors at the end, but it was a very large project team. So we wanted to explore the potential of using mass timber panels on the facade of a building, an existing building, to be able to upgrade this low-rise building stock, which is ubiquitous, for improved resilience and sustainability. So this you can see is a rendering of the process underway by which the existing facade is being removed on this low-rise commercial building and the new mass timber panels being installed. And why do this, you might think? Well, there are a few reasons we think this is a good idea. First, these panels can contribute as to part of a holistic seismic upgrade for earthquake resilience. They can improve the thermal enclosure of an existing building. They can provide resilience when the power grid is down by improving the illumination levels. By having better daylighting, you can potentially work even if the lights are off. You can add operable windows. A lot of these older buildings were built before there was operability in the windows, or before really when there was a zeitgeist of installing mechanical systems in every building. So by adding operable windows, we can have more resilience in these spaces. And you can have passive ventilation strategies. And frankly, some of these buildings are not that aesthetic, and you can upgrade the aesthetics and provide a more biophilic interior environment. We used a case study building in the Pacific Northwest. Oh, that moves. In the Pacific Northwest, this is a steel frame building, 4 stories, that we evaluated. And you can see in the left image, or on the left side of the image here, this is the structural system in the existing building and the lateral force resisting system. And the proposed upgrade would use the facade as part of that lateral force resisting system, in addition to some upgrades with rocking panels on the interior. So we spent a lot of time looking at the details, especially with working with Swinnerton, thinking about cost as an issue here. This is a rocking wall panel that was tested at the NERI, the tests in San Diego. The rocking wall was proven there, and so this has got the U-shaped flexural plates at the bottom, and it's got a post-tension assembly here that we used, and actually expressed the thread or the rods as part of the aesthetic. The interior, we also let the mass plywood panel, which is the panel we chose here, be exposed. And the reason we chose mass plywood is because the dimensions worked well for the proportions that we were going with. So this is a 7-inch mass plywood panel that's 4 stories for the rocking wall system. And then the non-rocking wall panels that were infill were 3-inch mass plywood panels. So here is an example of the rocking walls for the interior retrofit. They use a knife plate connection that's connected to the steel frame at each level through that knife plate. You can see on the right, it's a little small maybe. And then the window detail has been considered so that we could have peak 4% drift. So these have some seismic joints that are quite large. So the idea is that this building would have serviceability after an event, and we could have higher levels of resilience by being able to reoccupy that after a seismic event. One of the advantages of doing this is that we could remove the ACT ceilings and push up the head height. I'm looking at Siobhan Rockcastle, who with Baker Lighting Lab did these simulations. Alan Mahich in our lab also did simulations of the lighting. And by getting that higher head height for the windows, we got daylight deeper into the space and used shading to reduce the solar gain. So that was a big plus in this resilience upgrade, as well as providing an operable sash. These are fiberglass Cascadia windows that we used in this particular case study. So here's an example of that expression. There's more of a vertical expression due to the the rocking wall panels on the exterior facade, but we think it's a quite nice result with, of course, wood was what we chose for the expression here as well. We like that. And then the Energy Studies Lab looked at the envelope performance. This is the thermal improvement just by going to the mass plywood backer with 3 inches of mineral wool on the exterior of the rocking walls and 4 inches on the infill walls. We got 103% improvement over base case, which is an R14.5. We were using the ASHRAE guidelines to try and get to net zero ready for this building. So really a substantial improvement over code. And this building was the original one was built in the 80s. So, not that long ago, but quite a bit of thermal improvement. And the daylighting, this is the simulation that was done by Baker Lighting Lab, really shows that we got daylight deeper into the space. That first, it's maybe hard to see, that first image up here is spatial daylight autonomy. So more usable daylight throughout the year. 86% in the retrofit versus 54% in the as-built. We reduced the solar gain by dropping it down to 9% versus 13% in the as-built. And just the mean horizontal illuminance in lux went up from 547 to 784. So by doing that, we originally thought that we're going to increase the energy performance just by that thermal envelope, but quickly recognized that the lighting was a big component to the energy performance of this building. So adding better daylighting not only made it more resilient, it also had a 44% reduction in the electric lighting usage. So there's quite a few benefits, beyond just the seismic benefit, which is a big one if you do this retrofit. But many people will ask, what will it cost? What will it cost, right? Which is typically the questions. But luckily, we had Swinnerton do a very detailed cost model. And what they found was that just doing the seismic retrofit piece, and by the way, this was compared to a standard retrofit that was using BRB on that building that they had done. So they had some cost data from that retrofit that they could compare it to. And they found that just doing the mass timber in lieu of BRB, that retrofit was 14% of the cost for new core and shell at the time they did this analysis. And if we looked at the whole facade, which was not just the seismic components, but all of the other fenestration upgrades and cladding, everything, that was 26% of the cost of typical new construction of core and shell. And if we did include the whole interior fit out, if you wanted to do that at the same time, all of that together was 41% of the cost for new core and shell. So that is a substantial cost savings over new construction. So I think it makes a pretty strong argument for doing a facade retrofit, in addition to the embodied carbon, embodied impacts that you save by maintaining that building. We also think this is a pretty cool system that could be deployed for adaptive reuse projects and those applications, potentially changing programmatic functions for a building. We have a lot of urban cores that probably need new housing from office types, and potentially this could be something that could be explored. So with that, now I will show the long project team. We had, University of Oregon had a big team, number of students. Again, we worked with Siobhan Rockcastle and Alan Mahich in the Baker Lighting Lab, and then our Energy Studies and Buildings Lab was heavily involved in this project. Judith Scheim was a co-PI. Andre Barbosa was the co-PI here at Oregon State with Fernando Orozco, the PhD student that did all the modeling for this project, the seismic modeling. And then Swinnerton, I know that William Silva was here and had to leave a little early, but William Silva and John Smith were a big part of making sure that this was constructible and cost efficient. Judith was making sure that we stayed on budget the whole time and didn't, specify triple pane or quadruple pane windows for this project so that it actually made sense. And then FFA architecture, Edward Running, who's here, Ethan Bloom and Andrew Loya were hugely important to this project, did modeling and details. So this was a really great example of the way that we can work together with industry on these projects to create a really great outcome. All right.